All right, continuing on with parametric equations. Now we're going to get into some parametric equations with theta as a parameter. And we can link these a few ways. So for this one, we've got x equals 2 cosine theta and y equals 4 cosine theta. So I want us to make kind of two important connections here. The first one is, remember, we have this important equation for us, which was the unit circle, right, which was x squared plus y squared equals 1. Now, in the unit circle, we know, hopefully we remember, that x comes from cosine in the unit circle, right? That would be our x values, because of the triangle in the unit circle, our x would give us the adjacent side. Our sine gave us the y, right? Our opposite side over 1, again, in our unit circle, would give us that height. Now this is equal to 1. This comes so many things, right? This is our Pythagorean identity, which we could kind of use the unit circle to prove, but we talked about many things with that. So we're going to use this very important relationship whenever we're given parametric equations with just a plain old cosine and sine and this coefficient. So in order to sub them into these equations, I'm going to get cosine alone. So we'll have x over 2 equals cosine theta, and same thing for sine. So we'll have y over 4 equals sine of theta. Then we're going to take these and sub them into essentially our Pythagorean identity. So we'll have, maybe I won't simplify yet, x over 2 squared plus the quantity y over 4 squared equals 1. This will really give us this guy, which hopefully we are recognizing as the general form of an equation for an ellipse. So I can graph this. My A will be 4, my major axis. My B will be 2. My center is 0, 0. So from 0, 0, we're going to go to the right and left 2, because that's under our x. And we'll go up and down 4. And I'm going to draw in my ellipse. Now, no restrictions for this, right? We can put anything in for theta, for sine and cosine. But for orientation, until we see some patterns, I would just check some nice, easy points. So think about nice values for theta. I think 0 is a great one to start off with. Hopefully remember these guys. Cosine 0 is 1, so that's going to be a 2. Sine of 0 is 0. And how about pi over 2? Cosine pi over 2 is 0. Sine of pi over 2 is 1. So I'm subbing the theta value back into my original equations. So what this is telling me is that this guy, let's change back to our regular, is just like our unit circle. This is when theta is 0. Change that to a theta. This was when theta was pi over 2. So you guys should do some exploring if you like and see, like, when would our orientation change? Maybe you could think about that. Otherwise, there is my ellipse with our orientation. So you guys can try out some more examples. You can still graph these. And if you notice, we haven't graphed any conics really on our calculator yet. This is a nice, easy way for us to do that. If I clear, I think I'm in radian mode, so I'm good. So y equals, what was it for this one? I already flipped my page. 2 cosine theta. And x equals 4 sine theta. And I think I still have my window from -10 to 10. That should be good because we just need 2 pi, right, to go around a full circle. So I'll graph this guy, and there we go. Kind of cool way to graph an ellipse. And notice it's continuing on because I started at -10 and +10. So my circle kept going. So there's graphing our parametric equations with theta as our parameter.